Hey everybody. Today I'd like to just tie up a few loose ends as far as introduction to complex numbers, complex algebra, things like that. I'm not sure that any of these loose ends are directly related to any other loose ends, but I just want to mention these things because they are things that we should know, and I have yet to cover them. Now, the first thing we want to look at is the expression of a complex number as e to the power of a complex number. So e raised to the power of x plus iy. And if you think about this, using the laws of exponents, we can decompose this into e to the x times e to the yi. And if we're not immediately convinced of the truth of that, just remember that an equation is always a two-way street. Usually we read things from right to left, and unfortunately that goes for equations too. But an equation is a two-way street that can legitimately be read from right to left also. So if we have e to one power times e to another power, what do the exponents do? They add, don't they? And we get e to the power of x plus yi. So if we have e to the power of x plus yi, we can rewrite that as e to the power of x plus e to the power of yi. And e to the power of a real number times I can be represented as a linear combination of cosine and I sine. Specifically, the coefficient of I is going to be the angle at which we evaluate cosine and sine. So e to the x plus yi can be written as e to the x times cosine of y plus I sine of y. But since z, this number, can also be expressed in polar form as a magnitude or a modulus times cosine of theta plus I sine of theta, there are a number of things that we can equate here. E to the x has to be the same thing as r. Or we can write that x is natural log of r. And at first we might be a little apprehensive and say, well, wait a minute, what if r is negative? Can we just stick this in here? And the answer that I give is, when we represent z in polar form, r is positive. So this is a positive number. We stick it into the natural log function. No problem. And we can just as easily equate y with the angle theta. So if we have z written as e to the power of x plus yi, this does have an equivalent in polar form, and the modulus r is e to the x. Or we could say that x is natural log of r. But what I'd like to do now, just to get us comfortable with this expression, is just do a couple of conversions back and forth. Just a couple of examples, exercises, where we convert from polar to this form or from this form to polar form. Okay, example number 1. convert the complex number z, which equals e to the power of 5 plus 5 pi over 3I, to polar form. Okay, let's see what we got here. Z equals e to the 5th plus 5 pi over 3I. That we have e to the power of the sum of two numbers. We can break that up into the product of e to the 1st times e to the 2nd and this thing we recognize as being r, and so I guess we don't really have to do anything with that, do we? But there is something we can do with this. E to the power of some real number times I. We can represent this as a linear combination of cosine and sine. Cosine plus I sine and that's it. This is polar form. Well, that was painless. Let's go the other way. Okay, we're going the other way. We want to take this complex number given in polar form and write it in the form of e to the power of some complex number. So let's see what we got. Now, we've known for a while that this linear combination of sine and cosine is the same thing as e to the power of this angle, pi over 3, times I. This thing, well, it's in polar form, and in polar form, we express a complex number as a magnitude or a modulus times the sum of cosine and sine, or cosine and I sine, of a certain angle. So this thing has to be our modulus r. And do we remember e to the x is equal to our r? And so that would mean that x is natural log of r. So in this case, x would be natural log of 10. So we have natural log of 10. That's our r. Cosine pi over 3. plus I sine pi over 3. And we are almost there. Again, we recognize that this part this part is e to the pi over 3I. And this part, did I do that right? Did I do this right? 10 and natural log of 10 are not the same, are they? I have r here, so I have to replace r with its equivalent, which is e to the x, right? So what should go here is e to the x. Now let me ask you something. Does this look like e to the x to you? X is natural log of r. Does this look like e to the x? Doesn't look like e to the x to me. I think I need to change this. R, which is 10, is equal to e to the x, and x is natural log of r. So writing it as e to the x, I should write it as e to the x, which is natural log of r, and tell you what, I don't need that. Yeah, I do too. Natural log of r. I feel a lot better about this, and now I'll be able to sleep tonight and not have a guilty conscience. I guess now my next step is going to be to rewrite this in exponential form. So we'll have e to the natural log of r times e to the power of pi over 3I and we have e raised to 1 power times e raised to another power. What do the exponents do? Drum roll, please. They add, don't they? So this is e to the power of natural log of r plus pi over 3I. And there we have it. Just to summarize things, we'll write down our final result. Voila. Now, let's do one more example of this type, and let me throw a monkey wrench into the works. Okay, we're going to do a subtle variation on the exercise that we just did. At first glance, this probably looks exactly like the exercise that we just did. I just put one little twist there. The angle is the same, pi over 3. What's not the same is we have a negative sign out front here. No big deal. At least it doesn't seem like it's a big deal yet. So let's write down our z in polar form. And I look at this and I say, okay, here's my r. And let's see, I'm going to replace this with e to the x, where x is equal to the natural log of r. So that would be the natural log of negative 10. And all of a sudden, I realize things are not quite as easy as I'd like them to be. Natural log of negative 10, well, we can't do that. Or at least we can't do that yet. And if we're working with real numbers, we certainly can't do natural log of negative 10. In a course in complex analysis, we actually will work with the natural logarithm of a negative number, but we don't know about that yet. But we look at this thing and we do see that we have a problem. If we call this our r, then we're going to wind up letting x be the natural log of negative 10, and that's not something we know how to do, at least not yet. And looking at what we started out with, we might ask ourselves, was this really in polar form to begin with? Because in polar form, isn't r supposed to be the modulus of a complex number? Isn't r supposed to be the real part squared plus the imaginary part squared? This is the square root of a real number, a positive real number. We shouldn't get something negative here. X squared plus y squared is positive, and by convention, the square root function, which, since it's a function, can only return one value, the square root function returns the positive root. So r should be positive. So, I guess this wasn't really in polar form to begin with. So before I can write it in the form of z equals e to the x plus yi, maybe I need to do something to get this truly in polar form, where the coefficient out front, the real number out front, is a positive real number, and therefore it really can be the modulus of a complex number. So r, I look at this and I say, r my foot. I want my r to be a positive real number. So here's what I'm going to do. I'm going to write this as positive 10 times negative 1 times the cosine of pi over 3 plus I sine pi over 3. And it doesn't really look like I've done anything significant yet. But let's think about what this number is. In rectangular form, it's -1 plus 0i. But what if we were to take this thing and write it in polar form? It's easy to do because think of where -1 is in the xy plane. -1 is a point on the x-axis, 1 unit to the left of the origin. And if we wrote that in polar form, let's see, distance from the origin is 1. So our magnitude or our modulus is 1. And the angle is pi, isn't it? So what this is 1 times cosine of pi plus I sine of pi. And 1 times anything is just that thing, so we don't really need the 1 here. So this -1, what it is cosine of I times I sine of pi. And I'm going to make that replacement or that substitution in the next step. See, cosine of pi plus I sine of pi times all of this junk. And in polar form, multiplication is the easiest thing in the world. The angles just add, right? So we have 10 cosine of pi over 3 plus pi plus I sine pi over 3 plus pi. And that gives us 10 cosine of 4 pi over 3 plus I sine 4 pi over 3. And now this really is in polar form. This is r. And we remind ourselves that x equals natural log of r, or natural log of 10. And we like that. Natural log of a positive number, we're very comfortable with that. And this thing, that's just going to be e to the I theta, or e to the I times 4 pi over 3. And let me put this I in the back. E to the 4 pi over 3i. Oh my goodness. Okay. So here we should get r equals e to the natural log of x. So let's see, that's e to the natural log of 10. And over here, e to the 4 pi over 3i. E to 1 power times e to another power, e to the natural log of 10 plus 4 pi over 3 times I. Beautiful, beautiful. Next, we're going to talk about taking imaginary numbers, imaginary my foot. Next, we're going to talk about complex numbers that are equal, and applying the fact that two complex numbers are equal, have real parts that are equal and imaginary parts that are equal. And we're going to apply this to some interesting problems. Okay. Something that's about as profound as the fact that Ulysses S. Grant is buried in Grant's tomb. We have this statement. Two non-zero complex numbers are equal exactly when their real parts are equal and their imaginary parts are equal. So, for example, we have x plus yi, and that's equal to 5 plus 6i. That means that x has to equal 5. The two real parts are equal. And the two imaginary parts, y and 6, have to be equal. Now, we know that. Let's apply this principle to some exercises and get some interesting mathematical results that would not be obvious without taking this approach. This is a great exercise. They ask us to prove two identities. Cosine 3 theta is equal to cosine cubed theta minus 3 cosine theta times sine squared theta, which is not obvious. Even if we know a lot of trig identities, and we've proved a lot of identities in trigonometry, this identity is not obvious. Neither is this identity obvious. Sine of 3 theta equals 3 cosine squared theta sine theta minus sine cubed theta. Now, The person that designed this exercise was not completely heartless. They gave us an idea of how to approach proving these two identities. They tell us to cube cosine theta plus I sine theta. So let me try the complex variables approach first. Cosine theta plus I sine theta cubed. And when we cube a complex number in polar form, we cube the modulus. The modulus is just 1. And we multiply the angle by 3. So this is cosine 3 theta plus I sine of 3 theta. Well, I got cosine 3 theta, I got sine 3 theta. As far as all of this garbage, I don't know. Let's try this again. And for a second, forget what we know about raising a complex number to a power. We're cubing the sum of two things. That's going to give us 4 terms. We're going to get the first thing cubed. So that's cosine cubed theta. And then we're going to get 3 times the first thing squared times the second thing. So that's 3 times the first thing squared times the second thing. Then we're going to get 3 again. We're going to get 3 times the first thing times the second thing squared. So 3 times the first thing times the second thing squared and then we're going to get the second thing cubed. Well, maybe this looks like something. I have cosine cubed theta, okay. And let's see. I have I times this whole piece of junk. So let's see. I'll put the I at the end. Now I'll put the I at the first. I'm going to put I first here. And I have 3 cosine squared theta times sine theta now this term, I'm squaring I and I'm squaring sine of theta. If I square I, that gives me a factor of -1. I'll put that out front. And I have 3 cosine of theta. I have the I squared, that's -1. And I have sine of theta squared. Okay, now on to this thing. I'm going to cube I and I'm going to cube sine theta. I squared is -1, so I cubed is -1 times I. So I get -I when I cube I, and I'm going to cube sine of theta. Okay. This thing is cosine theta plus I sine theta cubed. And down here, this whole piece of junk is also cosine theta plus I sine of theta quantity cubed. The two things are equal, so I'm actually going to write that out. Cosine 3 theta plus I sine 3 theta is equal to this entire piece of junk down here. So cosine cubed theta plus I 3 cosine squared theta sine theta cosine squared theta sine theta minus 3 cosine theta sine squared theta minus I sine cubed theta. And then, whoops. Yeah, okay, I'm good with that. This complex number and this complex number are equal. So what has to be true? The real and complex parts have to be equal. The real parts of both complex numbers have to be equal. The imaginary parts of both complex numbers have to be equal. So I'm going to note that. Okay, on the left, the real part is cosine of 3 theta. And on the right, let's see. This term is real. And that term is real. So cosine cubed theta minus 3 cosine theta sine squared theta. This was the first identity that we wanted to establish. We equated real parts. Now let's look at the imaginary parts. On the left-hand side, we have I sine of 3 theta. So sine of 3 theta is the imaginary part on the left. And on the right, our imaginary parts are I 3 cosine squared theta sine theta and I sine cubed theta. So on the right, the imaginary part is 3 cosine squared theta sine theta minus this guy, sine cubed theta. Now, without using complex numbers, those identities would be a little bit harder to derive. But here we have it. That we just created 2 unknown trig identities using complex numbers. And that was such a good example. Let's do one more. How about this one? This looks like a good exercise. Confirm the identities. Cosine of 4 theta is cosine to the 4th theta minus 6 cosine squared theta sine squared theta plus sine to the 4th theta. And sine to the 4th theta is 4 cosine cubed theta sine theta minus 4 cosine theta sine cubed theta. And based on how we did the last exercise, and based on what we see here, we pretty much know the approach because we see cosine 4 theta, sine 4 theta, and we see a cosine to the 4th and a sine to the 4th, and we think, I know how we're going to do this. We're going to take cosine theta plus I sine theta and raise it to the 4th. And I think that's exactly what we should do. So, cosine theta plus I sine theta to the 4th. And one way we can do this is just to realize that if we have a number in polar form and we raise it to a power, we get the modulus to that power, and the modulus is 1. So we get 1 to the 4th times what's in here with each of the angles multiplied by 4. So we raise the modulus to the 4th power. We get 1 to the 4th, which is just 1. And we multiply each of these angles by 4. So we get cosine to the 4 theta plus I sine to the 4 theta. Now, we also want to multiply this out, so to speak, the traditional way. But this is a little bit harder than figuring out how we square the sum of two things or cube the sum of two things. So I'm going to hit the chicken switch here. And I'm going to use the binomial formula. Okay. This is our binomial formula. It tells us how to raise any binomial to the power of a non-negative integer. And I'm going to do that with cosine plus I sine theta. So let's see, cosine of theta plus I sine of theta to the 4th. So 4 corresponds to n here. We're going to get the sum from I equals 0 to n, where n is 4. And then we're going to get this binomial coefficient, n choose I, where n again is 4. And we get the first term to the n minus I. So cosine theta to the 4 minus I. And then we get the second term, I sine of theta. Ew. You know what? Sometimes lack of foresight will come and bite me in the rear end, and this is one of those things. I have an I here, square root of -1. I have an I here, which is the index of my sum. It's a different I. So what I'm going to do is just change my I, my index I, to a J, just to avoid confusion. Okay? So I have cosine of theta to the power of 4 minus j, where j is the index of my sum. And I have I, square root of -1i, sine theta, raised to the j power, where j is the index of my sum. Well, this is one I definitely should have done out in advance to avoid that ambiguity. I apologize. But, okay. No ambiguity now with I. I in this exercise is the square root of 1, square root of -1. And j is the index of my sum. And this is going to give us, let's see, when j is 0, I get 4 choose 0 cosine of theta to the 4 minus 0 is 4. And I'll put 4 minus 0 there. And I get I sine of theta to the 0. And we go down for I equal 1, or j equal 1 rather. When j is equal to 1, we have 4 choose 1. Cosine theta to 4 minus 1. And I sine of theta to the 1. Okay, we've taken care of I equal 1. Now j will equal 2. And we have 4 choose 2. Times cosine theta to the 4 minus 2. And we have I sine theta to the 2. That finishes the computation with I equal 2. Now we want I equal 3. And we have 4 choose 3. Cosine theta to the 4 minus 3. And I sine of theta to the 3. And now can we squeeze this last thing in here? I think we can. Finally, our index j is going to be equal to 4. So we'll have 4 choose 4. Cosine of theta to the 4 minus 4. And I sine theta to the 4. Oof, we have just barely enough room. Okay. Before I write any of this stuff out further, let me just remind all of us what this binomial coefficient is. N choose I, that's n factorial, or j. N choose j, that's n factorial, over j factorial times n minus j factorial. For choose 0, that's going to turn out to be 1. And we have cosine theta to the 4th, I sine theta to the 0. So I sine theta to the 0 is 1. So we have 1, 1, and cosine to the 4th. Next term, we have 4 choose 1. If we plug in 4 for n and 1 for j, this will work out to be 4. So 4 times cosine to the 4 minus 1, or cosine cubed, and I sine theta to the 1. So let me put this sine theta here. And this factor of I, let me just put it there. Next term, 4 choose 2. Now that may take some computation. 4 factorial over 2 factorial times 4 minus 2 factorial. See, 4 times 3 times 2 times 1, that's 24, isn't it? And 2 factorial is 2. And 2 factorial is 2. So 24 divided by 4 equals 6. So this thing is 6. And we have cosine theta squared and I sine theta squared. So I'll put the sine squared theta here. But I'm also squaring I, and the I squared is -1. So that means I have to change this plus sign to a negative sign, and that's my I squared. Okay, next term, 4 choose 3. If we plug 4 in for n and 3 in for j, we find that we get 4. So I'll have 4 and cosine of theta to the 4 minus 3 is just cosine of theta. And sine theta cubed, that's sine cubed theta. Now I have to cube I. I squared is -1, so I cubed is I squared times I, or negative I. So I'm going to put an I here. And for the negative, I'm just going to change that plus sign to a minus. And that leaves this last term. If I take 4 and plug it into this formula for both n and j, it turns out I'll get 1. So I have 4 choose 4 is 1. Cosine of theta to the 0 is 1. So I have 1 times 1 times I sine of theta to the 4th. Well, let's see, I to the 4th. I squared is -1. So I to the 4th is I squared times I squared, or -1 times -1, which is +1, times sine of theta to the 4th. Okay, gadzooks, we did it. Now notice, this thing is cosine of theta plus I sine of theta to the 4th. And this whole piece of garbage here is also cosine of theta plus I sine of theta to the 4th. We can equate those things. And that's exactly what I'm about to do now. Cosine of 4 theta plus I sine of 4 theta equals all of this junk. Cosine to the 4th theta plus 4 cosine cubed theta sine theta times I minus 6 cosine squared sine theta, sine squared, minus this guy, 4 cosine theta sine cubed theta I, plus this thing, sine to the 4th theta. Now, let me make sure I wrote that correctly so that I don't cut my own throat. Looks like I did. So now what do we do to establish these two identities? We compare real and imaginary parts, right? Okay, so I'll mention that. Well, cosine of 4 theta is the real part on the left. And on the right, let's see, cosine 4 theta is real. Minus 6 cosine squared theta sine squared theta is real. And sine to the 4th theta is real. Okay. Cosine to the 4th theta minus 6 cosine squared theta sine squared theta plus sine to the 4th theta. These are the real parts on both sides. Now the imaginary parts. This term has a coefficient of I, so sine 4 theta is the imaginary part on the left. And on the right, this term has a coefficient of I, and this term has a coefficient of I. So these two terms provide the imaginary part on the right, 4 cosine cubed theta sine theta minus 4 cosine theta sine cubed theta and let's just make sure we've done this correctly. This should match up with that. And it does, thank goodness. And this identity should match up with this one, if there's any justice in this world at all. Sine to the 4th theta, 4 cosine cubed theta sine theta minus 4 cosine theta sine cubed theta. Okay. In our complex variables or complex analysis laboratory, we have just created 2 new trig identities.